Welcome to Luvitex Engineering, where we sketch out the things that keep the industrial world moving. Now, let's start.
You ever wonder what's really going on inside all the high-tech gadgets and machines that shape our world? Well, hidden away from sight, there are these brilliant little components doing all the heavy lifting. Today, we're going to pull back the curtain on one of the most important but most overlooked of them all. I mean, think about an MRI scanner. The bed you lie on, it just glides in and out so smoothly, and it stops at the exact right spot, every single time. How in the world does it do that? What's the magic behind that kind of flawless control? Okay, or how about these medical pumps? They have to deliver a life-saving dose of medicine with just perfect precision. The movement has to be controlled down to the tiniest fraction of a millimeter. So again, what's the secret? Well, the answer to both questions is this elegant, simple piece of engineering. It's called a lead screw, and yeah, it's the unseen workhorse powering some of today's most advanced technology. So how does this thing actually work? Well, the principle behind it is beautifully simple. It's all about one thing: turning a twist into a perfectly straight line. At its core, a lead screw's entire job is to take rotary motion, the turning of a screw, and convert it into precise, straight-line, linear motion. It's one of the most fundamental building blocks of modern machinery. Now here's the best way to picture this, and I love this analogy. Just think of a simple ramp, an inclined plane that's been wrapped around a cylinder. That spiral ramp, that is the thread of the screw. And this shows the whole setup perfectly. It's just two parts, the screw and a nut that rides on it. You turn the screw, and the nut has no choice but to travel along those threads in a perfectly straight line. Turn it one way, it goes forward. Turn it the other, it comes right back. Simple, powerful, and incredibly precise.
But of course, it's not as simple as just grabbing any old screw from the hardware store. For an engineer, picking the right lead screw for a specific job, well, that involves making some really critical decisions. It's a real designer's dilemma. So, if you were designing that MRI machine, what would you need to think about? What questions would you have to answer to make sure your machine works absolutely perfectly?
It really boils down to a few key things. You've got thrust, that's just how much weight it can move. Then speed, how fast you need to go. Then you get into two really crucial measures of precision: accuracy and repeatability. And finally, a tiny but vital detail called backlash. Let's dig into those last three a bit more. Okay, let's get this straight, because it's a super common point of confusion. Accuracy is all about hitting the exact target. You aim for 10 millimeters, you get 10 millimeters. But repeatability is about consistency. It's about being able to return to the same spot over and over and over again. And for a lot of machines, being able to reliably hit that same spot is way more important than hitting a perfect number. So what about backlash? Well, think of it as that little bit of slop or play between the screw threads and the nut. When you change direction, there's a tiny moment where the screw is turning, but the nut hasn't moved yet. For high-precision stuff like a 3D printer or a CNC machine, you have got to minimize that backlash. It's absolutely essential for a clean, accurate result. All right, now we get to the really cool part. This is the secret sauce of lead screw design, a fundamental trade-off that every single engineer has to wrestle with. It's this constant battle between moving easily and holding on tight. So this whole thing really comes down to a choice between two things that you want, but that kind of fight against each other. And here's the choice. Do you want a system that's highly efficient, that moves with very little power? Or do you need a system that's self-locking, meaning if you cut the power, the nut stays exactly where it is and won't slip, even if there's a heavy load on it? The thing is, you can't perfectly maximize both. This tendency for a heavy load to just push the nut and turn the screw all on its own, that's called backdriving. Let's go back to our ramp analogy. A super steep ramp is easy to push something up. That's high efficiency. But if you let go, it's going to slide right back down. That's a high-efficiency system that backdrives. A self-locking screw, though, that's like a very shallow ramp. It takes more work to push up, but once it's there, it stays put. So what's actually happening here? Well, physically, it's just a battle between two angles. The lead angle, that's basically the steepness of our ramp, and the friction angle, that's the amount of grip between the materials. If the lead angle is steeper than the friction angle can handle, the screw will backdrive. But if friction wins, it self-locks. And you can really see this when you compare lead screws to their cousins, ball screws. Ball screws use little ball bearings, so they're incredibly efficient, up to 95%. But with so little friction, they almost always backdrive. Lead screws are less efficient, sure, but that inefficiency, that friction, that's not a bug, it's a feature.
it's exactly what gives them their amazing self-locking ability.
Now, of course, to maintain that perfect balance of grip and efficiency, these components need a little care. That friction we've been talking about needs proper maintenance to work the way it should.
So how do you know it's time for a tune-up? Well, your machine will pretty much tell you. Just listen for any grinding or squeaking sounds, or feel for it. Does it seem like it's having to work harder? Or just take a look. If you can see scratches or a bunch of dust and gunk packed in the threads, then yeah, it's time for a clean and lube.
And the process itself is really straightforward. The most important part? Clean the screw first. Get all that old grit out of there. Then just apply a thin, even layer of lubricant, wipe away any extra, and just run the machine back and forth a few times to spread it around. And hey, keeping a little log of when you did it can make a world of difference for performance and how long it lasts.
So there you have it, the lead screw, a simple, elegant solution for precise motion control that's just quietly powering the world around us. Now that you know its secret, that constant balancing act between efficiency and grip, where else will you see its influence? From 3D printers to car jacks, its principles are everywhere. What are you going to spot next?
Thanks for watching. For more industrial insights, check out our other videos. Don't forget to like, share, and subscribe to Luvitex Engineering.